and I'm going to be showing Specviz2d. So the first things we're going to do are just import a couple of things that we will need, mainly the Specviz2d class, and then a couple other things that will be useful later. We are also going to run this cell to suppress any warnings that might pop up, just because there's a couple warnings that generally pop up from like AstroPi model fitting on the back end that will clutter up the notebook a little bit if we don't ignore them. So I'm just going to suppress those. And then before I get into actually showing you this notebook, I wanted to just take a brief detour. So we've mentioned a few times that you can use Jdaviz locally in a notebook or Jupyter Lab, and it's also embeddable like on the web. So right now we are all using the JWebbinar platform on a machine hosted by the Space Telescope Science Institute. One of the other nice things that this lets us do is actually embed Jdaviz right in MAST. If you're not familiar with MAST, it's the Mikulski Archive for Space Telescopes, and that is where you can find data from HST, James Webb, and other missions that we host. So the data we're going to be using is a spectrum of a planetary nebula that came from a program that was verifying the near-spec wavelength calibration. So this was a very early program in JWST, and the data is public. And you can get this data from MAST. So I'm just going to click this link in the notebook, and that's going to take us to the MAST homepage. There are all sorts of search tools under here. If you go to this page, what we're going to be using is the MAST portal. This is kind of the mature legacy interface. This MAST search tab will take you to a more modern interface. But right now, the thing that we want to look at, that I want to show you, is only available through the portal interface. So this is the MAST portal. And what I'm going to show you is just, I happen to know the program ID of this, that this data came from. So I'm just going to put that in here and search by proposal ID. And I want to only look at level 3 data. And what I want to show you here is in the results. So we have this list of results that we've gotten from our search in MAST. We have buttons to like download the data products. But what I want to show you is this button here. There's a button that says visualize this data product in Jdaviz. So if your data that you found in your search results is compatible with one of the Jdaviz configurations that is currently supported in MAST, you can actually just click one of these buttons and open it directly in your web browser from MAST. So from the search results, but if I click to open this, you can see this is opened in a new tab. This Jdaviz in MAST implementation of Jdaviz. It's generally a version or two behind like the most recent standalone like release version of Jdaviz, because there are a couple things that need to be done to have it work in MAST, and extra testing to do and those sorts of things. But you can see here you get just the UI portion of Jdaviz right in your web browser, along with some information about this observation. And so you can do anything you can do from the user interface, the GUI, right here in your web browser. The downside is, we don't want you executing arbitrary code on the MAST machines, so you don't have the notebook cells available like you would locally to execute and write Python code. So you can do anything you can do from the GUI. You can open these plugins that you've seen in the other demos. You can zoom and select regions and all those sorts of things right here in the web browser. So, if you've looked at your search results a little bit in Jdaviz on MAST and explored the data, what you can do to get that data locally is if you click this Open Data in Jupyter button, this will save a notebook to your local directory that will have populated in the notebook the code to retrieve this data from MAST and then open it in Jdaviz just like you see here. Now, if you've done operations in the GUI already, for example, let's say you like selected a subset and you've zoomed in and all sorts of things, those things won't be reflected in the notebook that you get by downloading from this link. it's just the code to sort of download the data and start Jdaviz in that fresh state. So you won't really be able to preserve anything you've done in this quick look version of Jdaviz on the web, but it is nice to be able to explore your data before you actually download it locally. So I just wanted to emphasize that before we go into this notebook. And if you look in the notebook that I have for my demo, this commented out code, this is just an example. This is essentially what you would get if you downloaded from that mass version of Jdaviz, the notebook. So this is the code that would go get the data from mast for you and construct the local path that you can then put into Jdaviz and load your data. So we already have this data loaded on the platform. And so we can, just like you've seen in the other tutorials, start an instance of Specviz2d, load that data into it, and then we're going to show Specviz2d. So we run that, and we get something that looks very similar to what you just saw on the web in Mast. I did not pick exactly the same data, so if you notice that these lines are slightly different, that is why. Right, so we've loaded our data. We see Specviz2d just like we saw in Mast. We've been showing you loading data before you actually show Jdaviz, but you could, if you didn't load this data first, you can just show an empty version of Jdaviz, and you can, by clicking this import data button, you can straight through the GUI, the UI, import data from your local machine into Jdaviz. So you don't have to go through this load data call, but you can. Now, Brett and Jesse are very smart, and they showed that you can automatically show Jdaviz, like split out into a separate side tab. I did not do that, so most of what I'm going to be doing is in the UI anyway, so I'm hopefully not going to do too much scrolling up and down. Right, so we have our two-dimensional spectra. I want to emphasize that the one-dimensional spectrum down here, this did not come from a separate file. This was automatically generated with some default parameters by the spectral extraction plugin in Specviz2d. And you may have noticed when you ran the cell to open Jdaviz that it popped up a message essentially warning you of that and telling you that. So if we click this toggle logger overlay button, we can see those messages that have been sent to us. Kemi mentioned this, and we can see there's a message saying, good, the data loaded. And then there's a message telling us that the extracted 1D spectrum was generated automatically. You can go into the spectral extraction plugin, and if you want to do something more custom, you can do that. So that is what we're going to do in my tutorial. I will just note one quick thing. Down here, you can see there's a gap. This is just the gap between the two detectors for this instrument. So you can see there's actually no data here in this range. Just a quick note of the quirk of James Webb data with this instrument. So as you saw in the other tutorials, you can click this plugin menu and go to the plugins. Brett mentioned this as well, but you can also access all of these plugins via their APIs in the notebook. So the one we want is the spectral extraction plugin. So down here, I just assign the plugin API to this extract variable, and now I have access to that in the notebook. So the first thing I'm going to do is I want to open it. I can do that through the API with this open in tray command. And if I want to see all of the things that are accessible via the plugin API, I can call this dir, which is short for directory, command on the extract object that I have. So you can see open in tray. This opened the plugin in the tray for me, as I would expect. And then all of the things I can access via this API are listed here. So some of these are just properties that I can set. Some are actually methods. So the open in tray method I just called as a method versus something like background width, that would just be a parameter that I can set. So if we look at one of those, let's look at trace type. So if I just call extract.traceType, you can see this parameter tells you which option is currently selected, which is just a flat trace. This also tells you what the choices are. So I could choose flat, polynomial, Legendre, etc. Now I can set that from the API in the notebook. So I'm just going to change to a polynomial, and I want a fifth order polynomial. So I'm going to set those two things. Now, the rest of the stuff I'm going to explore with this plugin, I'm mostly going to do in the UI, but this is just to note that you could, if you want to reproduce your workflow, you can type out the API commands. Or, for example, another common thing to do is once you've messed around in the UI and kind of figured out what works for this data, if you then wanted to apply those same things to 20 more 2D spectra, you could replicate what you did in the UI in the API, and then you could run those for all 20 of your files or something like that. All right, so switching to focusing on the UI now. You can see the thing that is new here. Let me close this. So we had our two-dimensional spectra and we had our one-dimensional spectrum that was automatically extracted. When we have the plugin open, we're getting these orange preview marks. Now, in the one-dimensional viewer, the orange preview mark is the extracted spectrum. And you can see this is just perfectly overlaying right now the originally extracted spectrum, because we've not really changed any parameters that would affect the extracted spectrum. So we're just seeing the preview of exactly what we had with our default parameters. These preview marks in the two-dimensional viewer are context dependent, depending on which section of this plugin you are in. So what we're seeing right now is the central trace of our two-dimensional spectrum. If we were to scroll down to the background section, this now updates so that we can see what is being used as our background. So this is currently two-sided, and you can see the areas on the two-dimensional spectrum that are being used for your background. In addition to this dotted line is still just our central trace. And then if you go down to extraction, this section, this is showing again our central trace and also the width of the window that we are using to extract that 2D spectrum. So just something to note, this preview is changing depending on what section you're in. Now, in addition to what I showed in the notebook via the API, I said, let's do a fifth order polynomial. You can also change the initial guess for which pixel in the Y direction is where your spectrum is. And you can see as I'm changing things, this preview spectrum in the 1D viewer is changing on the fly. It's recalculating every time. The spectrum is being binned. So we have 20 bins and our window width is 6. We could increase that for, if we want to consider a wider range of pixels for our peak finding of where the central pixel of our trace is. And you can also change the peak finding method. So this is currently Gaussian. You could change to centroid or max. You may see, if you increase the number of bins, a warning that the trace fitting could be slow if you're not binning your data as much. And that makes sense. So we just want to, we tend to pop up warnings like this if you are changing things in a way that might make things slow, just so you know that it might take a minute, maybe not a minute, but more time to update. So I'm going to change a couple more things. This data is actually already background subtracted, so it doesn't really matter what we pick for our background subtraction. But I'm going to change to one-sided, and let's just say, I'm going to zoom in a little bit. Let's say I actually wanted this kind of gray region here. I could increase the separation between my central trace and the background region to kind of line it up over the region that I actually want. I could also increase the width of that background region. And in addition, you can swap between the average or the median for what you're calculating for your background. So then I should also note, let's see, you can also export these various quantities. So right now, these preview marks, these orange marks, they're just previews. You can also do things like export the trace as an actual data object that will show up in this data menu. You can also do that with the background image, the background spectrum, the background subtracted image. So you could get all of these things out as actual data items. So if I click export there, if I now go over to this data menu, you can see it's not currently shown in the viewer, but now there's this background subtracted data object in my data menu, and I could add that to the viewer and look at that instead. So once you have all of your parameters as you want them, let's change, sorry, I forgot to mention, you can also change between boxcar and horn extraction. So let's go to horn extraction and let's call this something else. By default, this data label matches what is already in the 1D spectrum viewer, and so it would overwrite that. Let us rename it something else so it's not overwriting, and we can see if they're any different. So now I have extracted, and you can see there's now an extra data object in this viewer. So if I close this to make the preview marks go away, now I can just compare the default parameter extraction with what I just did after changing some things. And if we zoom in, you can see in this particular case, it's not terribly different, but there are some minor differences. So let us get rid of the original one and just focus on our custom extraction. There are there's actually two plugins that you could potentially use for line fitting. The line analysis plugin just does some automatic quick fits using the AstroPi Specutils package. So to use that, we need to define a region of our spectrum that we are interested in. So I have clicked on this tool that lets me select a range of X values and clicked and dragged to create what we call a subset. Making a subset just tells the Jdaviz application that we are interested in a particular region of the data. So in the line analysis plugin, I can say that I'm actually interested in this data, and I want to look at the subset 1 spectral region. And now to answer the question of what this continuum subtraction is, now that I'm zoomed in a little more, you can see there's a little preview of what this is using for the continuum. And this is indeed just a linear fit based on these two regions that are highlighted in orange. So this is saying use the surrounding area of the subset that I have defined, and you can increase the width or decrease the width. The other thing that you can do is say that my spectrum was a little more complicated and I wanted to manually select some area for my my continuum. I could create a second subset. Let's just say that's my continuum, and then I could select that subset as my continuum. So now there's essentially a linear fit to that subset that I've defined, rather than just an automatically generated window around my line. So once I have my region of interest defined and my continuum defined, then that just feeds in, as I said, to some Specutils analysis functions on the back end to give you things like the line flux, the equivalent width, Gaussian, full width half max, and the centroid, etc. The other thing that you can do, so that is kind of a simplistic thing, just assuming you have one line that's a Gaussian, right? This particular feature, well, it doesn't quite look not quite that obvious here. My previous zoom, it kind of looked like there's a little bump here, so maybe this is actually two lines, one smaller and one larger. If you wanted to fit something more complicated like that, I'm not going to go through this in detail in this tutorial, but we do have this model fitting plugin where you can define model components. So this is from AstroPi modeling. So you could add, for example, two Gaussian components, G1 and G2. If you had two lines that you want to fit simultaneously, say I wanted to have a linear background, I could add a linear component. So I could have a linear component for the background and two Gaussians, and then edit the starting parameters of those. and do a fit to my region here using that. So you can do a more complicated fit in the plugin, in the model fitting plugin in Jdaviz, as well as just that automated line analysis plugin. A couple other things. You can get that data back out into the notebook. So actually, rather than this automatically generated data, I'm just going to edit this on the fly and just say I actually want out the custom fit that we did. So I can get that back out into the notebook, and you can see this object I get out is a specutil spectrum1d object, and this is what I extracted with the spectral extraction plugin using my custom parameters. So you could then analyze that using AstroPy model fitting in the notebook rather than doing it in the UI, and all sorts of other things like that. And then this last cell, which I did not run, this is just showing how to define a subset from the API, from the notebook, rather than in the GUI. So if I were to run this, we should see there's now another subset. Let me delete subset 1. And let's see, this is subset 2, subset 3. It ended up being blue as well, but we can see I've defined another subset from the notebook around another line.